science. If you have, let's say, two forces, F1 and F2, or T, and a third one, the weight. Those are forces that are along a physical system along ropes. So let's imagine here is a little guy with his arm and his leg, and he's being holding two strings, and it's at equilibrium. The purpose of the game is to get the tension along the left string and the tension along the right string. If we're not given any information about their directions, then the only way to solve for this problem is to know coordinate of the point along those ropes. Hence, if A, which is this point where the guy is 2 and 3, and let's say B here is, it's going to be bigger, so 4 and 7. And this guy, C, is -1 and 6. Then we can use that piece of information to deduce the magnitude, the direction of both forces F and T. So in this case, if we assume that the system is at equilibrium, then it means that the sum of all those forces is going to be equal to 0. That's pretty much Newton's first law. So whenever you see the keyword equilibrium, you know this is equivalent to the first law. For now, we're going to revisit that later on. That means all you have to do is express T, F, and W in component addition and add them up. The problem is if you do this, F in componentation has two unknown, Fx and Fy. T in componentation has two unknown, Tx and Ty. Let's imagine we know everything about W. So you have 4 known. We've seen as we apply Newton's first law that if we use this in 2D, you're going to get 2 equations. And you have 4 known, Fx, Fy, Tx, Ty. So there's no way we can solve for this problem. No way. We have 4 known, 2 equations. Ain't going to work. However, instead of expressing your force F and T in componentation, which will involve Fx, Fy, Tx, Ty, and hence 4 known, you can express F and T in unit vector notation. And we can do this because we know the direction of each. So again, if we know the direction of those forces, we can use unit vector notation and reduce all those unknowns by 1. Now the only unknown are F and T. So all we have to do is figure out the unit vector of each. So what do we observe? We observe that the position vector AB is parallel to the force F, since F is the tension along that rope. If F is parallel to AB, then naturally they share the same unit vector, because both of them would have a unit vector in the same direction. That's the unit vector EF, and that must be the unit vector of EAB. They have the same direction, and since by definition they have the same length, which is 1, they gotta be the same vector. Well, that's perfect, because now we can use the definition of unit vector and plug it in back in. This is vector F divided by its own magnitude. This is vector AB divided by its own magnitude. Therefore, vector F can be expressed by its magnitude, which is unknown, times its direction, which is known. Because now we know how to calculate the position vector. In this case, F will be unknown magnitude. Position vector AB is final minus initial, therefore 2 and 4. And we're going to divide by, again, square root of 20. Only one dude. Easy, nice. Similarly, we can do the same thing with T. T is parallel to AC. Therefore, they share the same unit vector. ET is equal to EAC. As we substitute the definition of unit vector, vector T divided by T is equal to vector AC divided by AC. Hence, vector T is equal to its magnitude T multiplied by the information about its direction, which is position vector AC divided by magnitude of AC, or the length. Hence, since we know how to calculate the position vector, vector T is equal to T times AC is going to be C minus A, so minus 1 minus 2, that's negative 3. And 6 minus 3 is positive 3, divided by 918. Up. Since W is obviously, if I pick the standard coordinate system, 0 and negative mg, whatever that is, now I can add all those. This one will give me a system of two equations to unknown. What is the x component of t? What is the first term? Negative 3 over square root of 18. What is the x component of f? Again, the first term here, plus 2. F divided by 20. What is the x component of w? 0. And I can do the same thing with the y. What is the y component of t? Well, obviously the second term, 3 divided by square root of 18. What is the y component of f? The second guy, plus 4 square root of 20. And the y component of the weight. I now have simply to solve a system of two equations to unknown, instead of dealing with fx, fy, tx, ty, which would have been 4 unknown, and only two equations. Okay, so that's the value of the unit vector and the unit vector notation. Always express a vector in unit vector notation if you happen to know its direction. So all you have to do is identify the vector that you're interested in and see if you know the points along the same direction. Then you know those two have the same unit vector. Okay?